Ever since the dawn of life on this bright blue marble we call Zera, almost all life has been confined to the planet's single global ocean. It has conquered almost all underwater habitats bar one. Freshwater. Rivers and streams that pour down from the mountaintops, large lakes and ponds fueled by equatorial storms, vast wetlands and swamps formed by the rain eroding away at the ground bit by bit. All of these habitats, while still mainly aquatic, act as the first stepping stone towards life on dry land. Freshwater habitats display a vastly different set of challenges compared to the salty marine ones of the ocean, yet life will find a way. Hi, welcome back to the ZIRA project. I'm Zachbot and I'll be your host for the evening. Like I've said previously, freshwater holds many challenges. Now, whilst most of them, like the salinity levels and the different amounts of minerals, won't have a visible effect on the organisms, some of them will, drastically. One challenge is sediment. The Pediazelli are some of the most prolific plants on Zera, plant analogues. So, with that being the case, you'd think they'd be some of the first colonizers of freshwater habitats, but you'd be wrong. Rivers and streams have strong flowing currents that brush away lighter sediment, leaving only heavy rocks behind. This becomes an issue for the Pediazelli as their main plant body remains under the seabed. This may allow the ancestral metiophyte, whose roots remain above the seabed, to have an upper hand in colonizing freshwater habitats. Introducing the dyscampy, meaning stiff plant. The dyscampyphytes fill a similar role to water reeds of Earth. Their roots are long, thin, and sprawl into all sorts of directions, allowing them to anchor themselves to whatever rock they find. As well as the roots, the leaves have undergone some changes as well. Unlike their ancestors, which leaves were broad and flat to maximize sunlight, the dyscampyphyte's leaves are thin, tall, and stiff. They have evolved this due to another challenge posed by adapting to freshwater ecosystems. Rivers and streams have constantly flowing currents. This means that large, flat surfaces act more like a sail than a leaf, dragging the plant along, and it would eventually end up washed out back in the ocean. To combat this issue, their leaves have foregone their flatter ancestral shape and are now stiffer and more cylindrical. This allows them to cut through the sharp currents instead of being dragged away by them, allowing the plant to remain where it is. Unlike their metiophyte ancestors, the dyscampyphyte's leaves aren't flat, meaning to maximize surface area, they'll have to use a different approach. Instead, they may evolve to have their leaves be incredibly tall. Dyscampyphyte leaves would form thick, tall groves, often poking just outside of the riverbanks. Both the cocoons and the larvae of the dyscampyphyte may also have to evolve some new adaptations to combat these flowing currents. The major issue posed against the cocoons is that their round shape may allow them to roll away by the current. To avoid this, dyscampyphyte cocoons are flat and pyramid-shaped. This encourages the water to run over the top instead of pushing it along. However, the larvae have undergone the most drastic changes. You see, plankton doesn't tend to do very well in freshwater, as by definition they can't swim against the current. This means the flowing water of rivers and streams tend to blow them back out into the ocean or at least downstream. This may cause dyscampyphyte larvae to evolve to crawl across the riverbed. They may evolve to become long and worm-like, allowing them to weave in and out of the adult's leaves. Instead of feeding on smaller plankton, since there isn't any, Dyscampy larvae may evolve to feed on waste and smaller bits of detritus that sink down to the riverbed. Their singular facial eye may develop, allowing them to see more clearer through the murky freshwater. This may also come alongside a size increase. This size increase may call for blood. This blood may be red and iron-based, similar to the trichinoas and all of their descendants, despite not actually being one. It would appear pink through their translucent skin, giving them an even more worm-like appearance. Another radiation of freshwater plants may evolve from an entirely separate lineage. Unlike most other metaphytes, the tristichophytes have far less control on their location. They float around, constantly being pushed around by the waves, and some of them may end up being washed into freshwater ecosystems. There, they may give rise to a new clade, the intacify, meaning tension plant. Lakes and ponds tend to be far smaller than large oceans and seas, so the intacify may be far smaller than its tristichophyte relatives. Their smaller size would make them fill a similar role to duckweeds of Earth, although some of the larger species would be more akin to lily pads. Their colonies would be able to quickly expand and cover most non-flowing freshwater ecosystems. Rivers and streams might be out of the question as they'd get blown downstream, but larger, stiller bodies of water like ponds and lakes would be up for grabs. The cocoons would be very similar to their larger ancestors, although they would be smaller, just simple pods that float about on the water's surface. However, the larva is where things will really start to get different. Adult intaciphytes may be too small for the larva to cling onto the underside realistically, so instead they may evolve to do something else. On Earth, some insects, like water striders or water skaters, have evolved to use surface tension to walk on water. This behavior may convergently evolve in the intaciphyte larva, allowing them to stay near the surface without clinging onto the parent's undersides. Because of this, they may convergently evolve a similar body plan to water skaters, with their limbs being long and thin. However, now that they're above the water, there's a new problem: drying out. For starters, they may evolve to better retain water by simply having thicker skin. But being able to retain water means nothing if you can't get it in the first place, so another adaptation may arise to allow them to maintain their moisture while still being above the waterline. All four of their limbs may evolve a simple groove underneath. This would allow water to travel up using capillary action. Capillary action is a phenomenon where water travels up long, thin tubes. It's something to do with gravity and surface tension, but I'm not a physicist. It just works, trust me. How it works isn't very important. What is important is that it allows water to travel up the groove in the leg towards the mouth located on the underside of the body. This means that intacify larvae essentially drink using their feet. Both of these new clades would quickly spread across the freshwater ecosystems of Zera, and these new plants would act as a new food source for some other creatures, causing some new colonists to emerge. When the tristichophytes began colonizing freshwater, they may have brought along some of their inhabitants with them. Many creatures would be too small or specialized to adapt to this change in habitat. However, the copurisas, being small and adaptable, may be able to eke out a living as freshwater herbivores. Introducing the Colonial, meaning water cavity, and we'll get to that name in a minute. The Colonial may face a similar challenge to the intaciphyte's larvae. The intaciphyte's root system might be too thin, small and flimsy to realistically support their weight. To get around this, they've evolved two strategies. One strategy is free swimming. Much like their distant Alexipiso ancestors, they could use gaps in their shell, called a siphuncle, to monitor their buoyancy and float up and down. If a threat is detected whilst they're swimming, they use their buoyancy to float up to the top of the water. They then retract all their body parts into their shell, much like their ancestors, and mimic the cocoons of the intaciphyte. This defensive mimicry causes the threat to mistake them for the cocoon and leave them be. Their second strategy, however, is far more unique. One of the cavities in their siphuncle may evolve to house water. The cavity would expand in size, increasing the volume of water it can store in its shell. But how does this solve the issue of not being able to cling onto the roots anymore, you may ask? Well, it could allow them to sit on top of the plant instead. Much like a frog on a lily pad, they may do this for many reasons. Maybe they're tired, maybe there's threats in the water, or maybe they just want to. However, their water cavity does not last forever. Eventually, they have to return underwater to refuel. And whilst they can maximize the amount of time they spend out of the water by retracting into their shell, it's not that effective and they still need to return to the water very often. Another change the Colonial could evolve is in diet. Their diet may expand from just algae to the roots and leaves of the intacifytes as well. To help break down these tougher tissues, they may evolve rows of teeth around each 6 of their throats. Their arms may also elongate, able to rip and tear leaves and roots of the intacifyte adults. Another herbivore may come from a much more familiar and cuter origin. Up until the evolution of the Cyparisas, the Parvosaurus have held dominion over almost all herbivorous niches. So, it's likely they'll have some freshwater representatives as well. Introducing the ischyropod, meaning strong foot. The ischyropod has evolved many new adaptations to cope with life in freshwater. For starters, their jaws are stronger and more muscular. This allows them to more easily rip and tear the reed-like leaves of the dyscampy, their main food source. Another adaptation they have evolved is jointed limbs and a split foot. These adaptations have evolved to help the ischyropod traverse fast-flowing currents. The ancestral legs of the Parvosaurus were thin and straight. This isn't very good for traversing rivers. Not only would their limbs not be strong enough to grip onto rock, but they would also struggle to reach shallower waters by crouching down. So, not only have their legs gotten far thicker and muscular, hence the name, meaning strong foot, but their legs have also evolved to be jointed, giving them far greater flexibility and allowing them to traverse more areas. Lastly, the ends of the legs, the feet, have split off into 2 simple toes, giving them greater dexterity and stability. Perhaps another herbivore could evolve to colonize freshwater, but to avoid competition, instead of eating the larger plants, they may evolve to eat the build-up of algae on the riverbed. The concamis seem like the most likely organisms to adapt to this niche, seeming as they already live on the seabed and suck up marine snow. They may give rise to a new clade, the ancatharoido, meaning thorny sucker. To reduce drag against the flowing waters, their shells may shrink and become smaller and dome-like. To protect from predators, the shell may evolve simple rows of spines. These spines would counteract the drawbacks of having the smaller shell, so although it's easier to fit in the mouth, you will really not want to do that. For greater suction ability, their arms have become shorter and flatter instead of longer and more tentacle-like. This allows them to produce a simple cup underneath themselves, suctioning themselves to flat rocks. This makes it so it's incredibly hard for a predator to reach their soft undersides. But it also doubles as a way of gathering extra algae. It's a win-win. But what about the algae that isn't caught on the rocks or roots? What about the algae and debris and waste that's floating around in the stagnant waters? Whilst yes, rivers and streams would push away most of these particles, lakes, ponds, and just slow-moving rivers may be able to retain these in sufficient amounts. Perhaps a clade of free-swimming filter feeder may evolve to consume these. Perhaps the Sminaliso, the small and abundant schoolers of the open ocean, may adapt to fulfill this niche. Introducing the Asteropotami, meaning river constellation. These tiny filter feeders would live in massive swarms. They would be most common in lakes and ponds, although some could be found in slow-moving streams. However, living in these types of habitats has drawbacks. The lack of strong flows causes sediment to build up. This build-up of sediment causes the water to become brown and murky. This obstructs vision, causing many creatures to find alternatives to sight. Perhaps the Asteropatami could evolve their many face tendrils into chemoreceptive organs. Sensitive smelling and tasting receptors could line their tentacles. This may allow them to smell and taste their way around the murky waters instead of relying on sight. However, their deep-sea dwelling ancestors, the Sminaliso, evolved a separate method. If you recall correctly, the Sminaliso has bioluminescence. This trait will be carried over to their freshwater representatives, allowing them to use it when the water isn't as murky but it's still quite dark. However, in the murkiest parts of the waters, it could be used offensively. Suspended particles of mud, silt and sand could act as tiny mirrors. It could amplify their bioluminescence, confusing, stunning, or even blinding threats. Perhaps another clade of filter feeder could adapt to freshwater, although in an entirely different fashion. Currently, ZIRA filter feeders are incredibly diverse, occupying a wide range of sizes, shapes, behaviors and habitats. However, this competition may mean some of the primitive ancestral Imperial may begin losing ground. Both oceanic and freshwater habitats currently have stable ecosystems, so to avoid competition, they may evolve to live in between. These brackish water-living Imperial may become some of the last of the true Imperial lineage, and thus may have to adapt to this new lifestyle. This clade may be called the PS Makami, meaning pressed tentacles. Brackish water is where salt water meets freshwater. Both mangrove and coastal swamps fit this description, and it's where the PS Makami will reside, for most of their life. I say most due to a unique behavior of the PS Makami. On Earth, some fish, like salmon for example, have a unique life cycle where they spend part of their life in freshwater before migrating to the salty ocean. This type of behavior could be perfect for our PS Makami, as the increased competition may cause their young to be especially vulnerable. This may mean they spend most of their adult lives in brackish or even salty waters, but when it's time to mate, they swim upstream to find a suitable nursing ground for their young. A calm, tranquil lake could act as the perfect nursery for their children, and once they mature, they swim back downstream and continue the cycle. Swimming upstream and against the current would mean the PS Makami would need to reduce drag anywhere possible. To do this, their mouth tendrils could evolve to be flatter and pressed together, acting like a knife cutting through the water. Their fins and overall body would also increase in musculature, allowing them to do powerful strides up rivers and leap out of the water. All of this prey may cause some carnivores to adapt to freshwater habitats as well, and perhaps there is no greater candidate than the Acmerostoma. This family has evolved dominion over almost all predatory niches in Zera's oceans, so it's likely they'll also be the candidates for the apex predator of freshwater habitats. Introducing the Electrocheneftis, meaning electricity detector. Much like with the Asteropatami, the Electrocheneftis may have to evolve some new senses to cope with freshwater habitats. For starters, they may evolve enhanced mechanoreception, or touch. Their bottom two mandibles could evolve long, hair-like structures on their tips. These would be able to detect delicate vibrations in the water, allowing them to detect their prey's movements. This may not be enough, however, so on top of their mechanoreception, they may evolve something else, something entirely new and unbefore seen on Zera. Electroreception is where specialized organs in an animal's body allow them to detect changes in electric fields, or even electric fields themselves. So, these freshwater achimeristomes may evolve just this. Electroreception would allow them to sense their prey's nervous systems before the prey can even think that they're in danger. And coupled with this special ability, they may also evolve a new powerful weapon. Their mechano and electroreceptors would allow them to precisely pinpoint where exactly their prey is. So using this, their top mandible could evolve into a sharp harpoon-like structure. Specialized ligaments and muscles may evolve to hold it in place. They could hold it in place folded back before firing it forward at lightning speeds, impaling their prey's side. And if the initial harpoon strike doesn't instantly kill the prey, the bottom two mandibles will finish the job. But what if this electricity could be used for a different purpose? Not detecting their prey, but actually killing it. This clade could be called dyscampy, meaning shading lightning. This clade's electroreceptive organs could evolve into electrokinetic organs. Much like an electric eel, the dyscampy could generate powerful shocks in the water, killing, stunning, or paralyzing its prey before consumption. Whilst the top mandible may still be used for attacking, the bottom two could specialize for breaking down food. The singular large tooth on each mandible could partially internalize. Only smaller serrations would exist on the outside, acting like normal teeth for shredding and cutting their food. Perhaps, instead of detecting their prey and following them, they lure the prey straight to them. On Earth, canopy fishing is a special method used by certain birds. It's a hunting technique where they use their wings to cast a vast shadow on the water. This shadow lures in prey seeking shelter or shade. Perhaps the dyscampy could use their large ray-shaped bodies to do the same. They could lie in wait, floating on top of the water's surface, possibly even mimicking the intacify. And once prey crawls or swims close enough in search of shade or shelter, they strike using their electricity-generating organs, paralyzing, stunning, killing, and then eating their prey. This unique hunting strategy of canopy fishing could allow them to also niche partition with the electrocheneftis. The dyscampy could hunt at the water's surface, while the electrocheneftis could hunt near the sediment at the bottom. As we look around the new Zeran freshwater ecosystems, we see some truly strange, unique, and bizarre creatures. But if you want to see something truly amazing, you'll have to look just above the waterline. In the next episode, we'll discuss how Zeran life takes its first humble steps onto land. Thank you to everyone who has watched this far. It means a lot to me and I greatly appreciate it. This project owes itself to its viewers, but none more so than its amazing fan artists. Again, thank you so much. Don't forget to like and subscribe and all that jazz. See you in the next one.